and this is Physics 2, Lab 2, Charge Tapes Revisited. So, to introduce this lab, the purpose of it is to investigate the results of Lab 1 via a more precise computational model for finding electric force and charge. So, this lab is kind of an extension of the previous one. It uses some of the data we collected from the past one, and we're just comparing it with what we're going to find in this new one. So, the model changes in that the model, or tape, is now modeled as a line of point charges instead of just a single point charge, which we hope to, create a more accurate result thus. And then principles. So we use the same principles as last time. We have Coulomb's law, which would be the electric force is equal to K charge 1 charge 2 um, times R hat divided by um, R squared. And then we have the electric field, which we get based off superposition, which would just be E net is equal to however many E fields we have all at that observation point. And then Newton's second law is used again, F or force equals mass times acceleration. But in this case, we're going to be using it for gravity. So it'd be force equals negative mass G. And then preview. So a preview of our results would be that the magnitude of Q is found to be 2.20615 times 10 to the negative fourth newtons. So that is the new charge that we get compared to the other one. Okay, so lab conditions. So we are to assume that there is no air resistance, the U-tapes have the same beginning charge and end charge for that matter, and that the charge is evenly distributed amongst the entire length of the tape. System. The system is once again the charge tapes, and the surroundings are everything else. The initial conditions that we're going off of to simplify this model is that the initial charge of the two pieces of tape is 0. So now for the code. So here we get a quick preview of our code, or the result of our code, which is magnitude of electric force is, as we found in the preview, the magnitude of gravitational force is here, and then the magnitude of a single piece of tape is the following. So now let's take a look at the program and find some differences between our previous code and this new code. So differences starting off the bat would be our line charge, which this function that we add to it basically just creates of charges across the entire length of the tape. They're all equidistant, and that's what we mean by they are uniformly distributed. The equation for E field is just like we had in the other one, where you take your charge and then you find your R, which is observation location minus charge particle. You find your R mag, your R hat, and then you plug that into the equation, which is KQ divided by R squared R hat. Then we have our line charge again, which gives us our line. And then we just define a whole bunch of arrows and all the other stuff. But specifically, our electric force will be the magnitude of the top arrows, and then our gravitational force should be the magnitude of the bottom arrows. And when you do that, they both should be to the same scale, but unfortunately, and you all can choose to grade it how you'd like, but unfortunately, my model is having issues with the bottom arrows, so we'll leave it as so. But let's get back to the presentation. Comparison and sources of error. So modeling the tape as a line of point charges is more accurate than modeling it as a single point because uh, the uniform charge, quote unquote, is going to accurately reflect the entire length of the tape versus the other because charges will obviously be spread out along the entire length. And then or other sources of error would be other sources acting on the charge tape than those parameterized in the code. In the code, we have no other forces acting on the tape. At least that's how I've defined it. And then the tapes they have equal charge. In our example, we have the charges equidistant and uniformly distributed throughout the entire piece of the tape, and that they both are equal. But it may not be the case because if you pull them off, like the lab experiment does with stripping the two pieces of tape to charge them, then they may not result in equal charge. And then what if and what does it mean? So what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use the experimental data to produce a point charge value to the value you get with the line charge. So if we look back at the results of our code, we're able to see that our charge value is nearly double what the charge was of the other one was, because we have 2.2 to 1.32. So the way that we've calculated code in this one, or calculated charge in this one, has made it so the charge of the point charge model is less than the charge of the line charge model. And why do these estimates differ? Well, which value is more likely to be closer to the real value and why? So these estimates differ based on how we treated the model and how we treat the tape as a singular point charge versus how we treat the tape as an entire length of an object. And the second one is closer to the real value because it more accurately models the tape, meaning it'll more accurately model the distribution of electrons and charge in it. meaning that you'll get a more accurate charge per thing. And then conclusion. As I've reiterated at verbatim, charges is more accurate than treating it as a single point charge, and point charges do not model the charge distribution of large objects well, because it's a singular point versus the 0.2 meter piece of tape that we had. Okay, that's everything.